So DC motor is a self-controlled device. DC motor is self-controlled device. How it is a self-controlled device? So let us explain how it is a self-controlled device. So in the last class we have observed that the armature current equation as V minus EB divided by IA. So here EB is equals to phi NZ by 60 into P by A. For the given machine, once the machine is designed, so the back EMF is directly proportional to product of phi into N. So if you are keeping the flux as also constant, so it is directly proportional to, I can say, back EMF is proportional to N. So how the N will be changed? How the N will be changes? If, see here, if load is increased, let us assume that if load is increased, that means the speed will be decreases. If the speed will be decreases, what will happens? The back EMF will be decreases. So if the back EMF is decreases, what will happens to the armature current? So armature current will be increases. That means the motor will take extra mechanical power. So motor will take the extra electrical power to overcome that, okay, to handle that extra, okay. So it will take some extra electrical input for the motor. So whenever you are decreasing the back EMF, so what is happening? You are getting the you have to take the extra electrical input. So in this, if you consider the another case, if load is decreased, let us assume that if load is decreased means, so the speed will be, what will happen? The speed will be increases. If the speed is increases, so what will happen? The back EMF is also increases. So once again, let us write here, IA is equals to V minus EB divided by RA. If back EMF is increases, what will happen? So the armature current will be decreases. And that means the power, electrical power, what it is taken by the motor will be decreases. Here it will be, here you can write here, it will be increases. So that is why, that's why the motor is a DC motor is a self-controlled device, okay. Whenever it is required, it will take the electrical input. Whenever it is less required, it will simply leave the electrical input. So that's why the DC motor is a self-controlled device. It is known as the self-controlled device. That is the explanation for the last point in the last video. Let us come for the actual topic. So now we will see what is the torque equation of DC motor. Torque equation of DC motor, very important derivation for the external exam. And see the previous one. So this question is very important. How the question is, they will ask what is the importance of back EMF. The question they will ask, what is the importance of back EMF in DC motor. So that is the importance. This, because of this back EMF only, it is acting like a self-controlled device, okay. Next you see, so torque equation of DC motor. In case of torque equation, first of all let us understand what is the meaning of the torque. So torque means twisting movement. Torque is the twisting movement about an axis. Torque is the twisting movement about an axis. Torque is the twisting movement about an axis. So in case of the DC motor, if you observe, in case of DC motor, you have the rotor will be like this. You have the rotor and it is an axis, that is a shaft here, or shaft will be present. So having the radius of R, let us consider the radius of this armature will be R. So because it is having the radius of R, okay, and it is rotating, let us assume, and it is experiencing some force. We have already seen like this, okay. It is rotating means, so it is a twisting movement. So this is an axis, so this is the axis here. So there is a twisting movement about this axis, that axis is the shaft here. So that is called as the torque. Torque is the twisting movement about an axis, we can call it as the torque here. So we know already what is the force present on the conductor is, here is B into IL sin theta, where theta is the angle between I and B, we are already seen. Let us assume the terminology what we are using. R is the radius of armature. R is the radius of armature in meters. Next, L is the effective length. L is the effective length of conductor in meters. Once again, L is the effective length of the conductor in meters. Next, Z is the total number of conductors. Z is the total number of conductors. Next, A is the number of parallel paths. A is the number of parallel paths. Next, phi is the flux per pole. Phi is the flux per pole. Next, P is the number of poles. P is the number of poles. And here IA is the total armature current. Total armature current. And small I is the current in each parallel path. Current in each parallel path. Current in each parallel path, that is IA, that is total armature current divided by A. And B is the average flux density. B is the average flux density. So flux density we can calculate it as flux per pole, okay, flux per pole divided by area under each pole. Area under the each pole. So this is the flux density. So flux density will be the quantity divided by the area. So here the flux density, average flux density is flux per pole under divided by area under the each pole. Let us see what is the area under the each pole. So if you consider the poles will be like this. Let us assume the poles will be like this. So if you have the poles like this, having the poles, so this is one pole we are taking. Under this we have the armature will be there. So armature is rotating. Under this, how much of conductors it is covered. So whenever the area under this is the area is covered by the pole, one pole, right? So let us write. So what is the flux density? We can write the flux density value, we can write as, so flux per pole is, flux per pole, that is phi we have taken, divided by what is the area covered. So this is the length will be there, like this we have so many number of armature slots will be there like this. That means total effective length will be L we have taken. So and it is covering the total circumference, okay, the total circumference it is rotating, okay, total circumference. So that's why you are going to get it as, we can write. So what is the area under each pole is, how much it is, 2 pi r, that is the circumference, and total length, effective length of the all conductors L divided by pole, per pole we are taking, okay. So 2 pi RL, well, how you got? 2 pi RL is the circumference of the total armature. Next it is having the effective length is L, okay, that's why we are multiplied the total area. Next per pole, okay, flux density, area under the each pole. So how many number of poles are there? That many. So for example, here also one pole will be there like this. So let us like this, you have the one pole, you have the another pole like this. So many number of poles will be there, na? So depending upon that, the pole will be divided like this. So divided by P we have written. So let us, we can write that the flux density B we can write as P phi by 2 pi R into L. So now force on each conductor, we are already know what is the force. Force on each conductor, force on each conductor will be, that is F is equals to B I, that is B I L newtons, B I L newtons. Next, torque we can write as torque due to one conductor. Torque due to one conductor is equals to, we can write as F into R. F into R. So total armature torque we can write as total armature torque, we can write it as how many number of conductors we are assumed? Z. So Z into F into R we can write. So let us substitute Z into BIL, that is the force, and into R. So and Z into small I we have taken it as Ia by A. Next, the flux density you got it as 5P by 2 pi RL, and into next it is I we have substituted, next B we have substituted, next you have the L will be there and R will be like that only. So just what I am telling here, I am substituted equation 1 and equation 2, okay, equation 1 and 2 in 3, okay, equation 1 and 2 in 3, okay now. So if you written like this, so what you will get, so here R, L will get cancelled, and finally you will have, we can write as 1 by 2 pi phi Ia into Z P, okay, P by A. Finally we have like this. So what we can write the torque equation, final torque equation we can write as the armature torque. Torque, that is you got it as, that is the armature torque, we can write as 0.159. 1 by 2 pi value will be 0.159 phi Z Ia into P by A. Very important for your problems, very important for your problems. So the problems will be asked based on this formula. This is the armature torque. Now let us calculate what is the relation between the back EMF and this. Back EMF we can write it as phi NZ by 60 into P by A. So here you can observe what is the 60 into EB divided by N. If you write, we can write it as phi Z P by A. This is the remaining term, phi Z P by A. So we can replace, so you substitute this equation, okay. Let us consider the equation 4. In equation number, so this you take it as 4, this you take it as 5. Substitute equation 5 in 4, what you will get? So the armature torque you will get it as 0.159 phi Z P by A. Instead of that we can write it as what? So Ia will be there like that only, so Ia will be that only. So instead of that we can phi Z P by A. So what we can write? 0.159 into Ia phi Z P by A. Instead of that you can write as 60 into EB by N. So finally if you multiply 60 into, we will get it as the armature torque is 9.55 into EB into Ia divided by N. This is also one more formula, this is also one more formula you have to remember, very important. The armature torque will be 9.55 into back EMF into Ia divided by N, like this also we can write. So let us come for the another torque. Another torque is also there. Another torque, whenever you have taken the armature torque will be like this. So armature torque, and you have finally we are taking the torque from the shaft. So this is called as the shaft torque, okay. So this is the shaft torque you are getting here, and this is the armature torque, and the middle you have the some losses will be there, that losses. So that losses is friction and windage losses, friction and windage losses, friction and windage losses. So how to get these losses is, so these losses are known as the loss torque, okay. Sometimes they will ask the loss torque also. How we will get the loss torque? So loss torque we will going to get it as TA minus T sh. So we can write as Ta minus TSH, and 9.55. So what is the power output here? So friction and windage losses are not. So friction and windage losses, which is in the watts, windage losses, so divided by N. Okay, so friction and windage losses divided by N is equals to, we are going to write as armature torque minus shaft torque. Now we can calculate the shaft torque also. So shaft torque means how much of we are taking the output here. Let us see what is the shaft torque. For calculation of the shaft torque, work done for one revolution, work done for one revolution, we can calculate as force into distance moved, in one revolution, force into distance moved in one revolution, So we can write as force into, what is the distance moved in one revolution? That is 2 pi r. So we can write as 2 pi into F into R. So 2 pi into F into R we can write as shaft torque. Okay, so the shaft torque. So now finally we can write work done per second, we can write it as, that is 2 pi into TSH into N by 60. The units is joules per second, or watts, we can write as or watts also. So you can convert this as into output power. This is the output power, and output power you can convert into HP also. So 2 pi N SH TSH divided by 60 into 746.6. So to convert this horsepower. So this is known as the, so the shaft torque is also known as, so brake horsepower, we can write as brake horsepower. So this is the complete information. And if you observe the armature torque equation, some observations you have to note down. So the armature torque will be 0.159 phi into Ia into Z into P by A. This is the equation we got. So if you once the machine is designed, this number of conductors and P by A is a constant. So you will have, this is also a constant, you will have the armature torque is proportional to phi into A. Very important equation while studying the characteristics of DC motors. So armature torque is proportional to the product of flux and the armature current. In the case of shunt motor, I will explain shunt motor later. In case of shunt motor, the flux is constant, so armature torque will be proportional to only armature current. In case of series motor, what will happen? The flux is proportional to armature current only, because all are equals to series field current. So armature torque will be proportional to Ia square. So based on this, we are going to use, so different applications, for different applications we are going to use either shunt motor or series motor we are going to use. Very important relation you have to remember. That's all for today's class. In the next video we will see what are the different types of DC motors and what is the applications of different types of DC motors. If you are seeing the first time this channel, please like, share and subscribe the channel, which is very useful for your friends, so to prepare the external exams. Thank you very much.